some of the things that are coming up. Quiz 3, take-home quiz 3 is due next class on Friday. Covers classes 26 through 30, so after today's class, you should be able to do anything that you weren't able to do before. And then next week, Project 4 is due on Wednesday, and the week after that, we have Test 3 on Monday, the 5th. And the review class for that test is gone, so you will be getting the rest of Packet 3 on Friday, and it will have 2 study guides in it. Both of those study guides will have video solutions to help you review on your own. And this Friday afternoon, I'll have some extra office hours. So you can stay after class. Finish teaching at noon, so I'll stay like till 3 or 4 if you want to come ask questions. Okay, so in this section, we're going to see our last tests for convergence. We're going to start with the concept of absolute convergence. Okay, so this test says that if the sum of the absolute values of all the terms converges, then the sum of the terms without absolute value also converges. So let's take a quick look at this alternating series. We have the sum from n equals 1 to infinity of -1 to the n over n squared. So if I plug, I'm going to write out the first few terms. If I plug in a 1 for n, I get -1. Right? -1 to the first is -1 over 1 squared. And then my next term, when I plug in an n equals 2, that -1 squared becomes a +1, and I get a fourth. And then when I plug in n equals 3, -1 cubed is -1, and 3 squared is 9. So this becomes -1/9. And then when I plug in a 4, -1 to the fourth becomes +1 over 16. So this is +1/16. And then it will be -1/25 plus 1 over 36 minus ... All right, so if we think about this series in absolute value, if everything was pluses, we already know that that series converges. So, which means that its sum is finite. And if I make some of the terms negative, that sum is going to become smaller, right? Smaller than something finite, still finite. Okay, so this has to converge. Because 1 plus a fourth plus a ninth plus a 16th converges. Okay, so if all the terms, when they're positive, converges, then if you make some of them negative, it will also converge. Okay. All right, so hopefully that makes sense now that we've done an example. The second test we're going to look at is the alternating series test. So if the terms alternate positive, negative, and the terms are getting smaller, and the terms are approaching 0. So if the terms are getting smaller and smaller and smaller and approaching 0, and they alternate sign, you can conclude convergence. So I could have used this test on the one we just did, right? My terms are alternating sign, okay, negative, positive, negative, positive. And the terms themselves, without considering the sign, right, are decreasing. They're getting smaller and approaching 0. So the alternating series test would also say that this converges. So the rationale for the alternating series test is this diagram, right? So if you take away the alternating signs, terms getting smaller and going to 0 is not enough to conclude convergence, right? That we have a test for divergence that if the terms are getting smaller and going to 0, it might converge, right? But if we add this one stipulation that the signs alternate, then we can conclude convergence. So here's a little number line, right? If you put A1, say your first term is positive, and then I'm just going to do my partial sums. So this is S1 right here, right? A1 is some positive term, so my first partial sum is just A1. And then your second partial sum is A1 plus A2. And when you add A2, A2 is negative, so it goes the other way, but it's smaller than A1, so it doesn't go quite as all the way back to where it started. And you get S2. And then you add A3, which goes in the other direction, but it's smaller than A2 was, and you get the third partial sum. Then you add the fourth term to get the fourth partial sum, and you get S4, and it's going to keep narrowing in on some particular sum, some convergent value. Okay, so if I write out the first 5 terms of each of these series, I want to determine whether or not they converge. Okay, so let's see, if I plug in a 1 here, I get 1. Because n plus 1 is 2. When I take -1 and square it, you get +1 divided by 1. All right, and then plug in a 2, I get -1 cubed, which is -1. And the bottom is a half. Okay, and then I'm going to plug in an n equals 3. So 3 plus 1 is 4, so that's going to be positive. -1 to the 4th is +1. 1/4. And then plug in a 4, and I get a -1/5 plus 1/6 minus 1/7 plus ... Okay. Did I miss a term? Oh, yeah. Thank you. So when the signs weren't alternating, what was this series called? The harmonic series. And now the signs are alternating, so we call it the alternating harmonic series. So what do you think? Do we have convergence? So we could try our first test, right? We could look at our first test and say, well, let's look at the absolute value of the terms. So I would say 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. If that converges, so does this. Does that converge? Anybody remember? No. So that first test doesn't help us. Doesn't tell us anything. That test just says that if that does converge, we would know this converges. This doesn't converge, so it doesn't tell us anything. No help with that test. But this is an alternating series. The signs are alternating. And the terms are getting smaller and approaching 0. So that shows convergence. Okay, if you show all of those things, signs are alternating and the terms are getting smaller and going to 0. Then you have convergence. All right, let's write out a few terms of this next one. -1 to the n times n over n plus 1. So when I plug in n equals 1, I'm going to get a negative. And when I plug in a 1 for n, I get a half. And then plug in n equals 2, and I get -1 squared, which is +1. And then I get 2/3. And then when I plug in n equals 3, it's going to be negative. And I'm going to get 3/4. plug in n equals 4, and I'll get a positive 4/5 minus 5/6 plus 6/7. What do you think? Ideas? Thoughts? What? You think it diverges? How come? Yeah, the terms are getting bigger, right? Yeah. So we have a test for divergence. It says that if your terms don't go to 0, you have no chance of converging, right? A half, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. Those are getting bigger, right? So we have no chance of a sub n's don't go to 0, which means it has to diverge. So for alternating series, when the signs alternate, there's an easy formula to figure out the error of cutting off the series after n terms, right? So you can't possibly add up an infinite number of terms by typing in your calculator. Sometimes we can do something tricky to figure out what the infinite sum is. But usually we take partial sums, and partial sums are estimates, better and better estimates of the entire infinite sum. So if you take a partial sum that includes only n terms, a finite number of terms, the error approximated by that sum of using only n terms instead of all the terms is at most the next term in the list. So if I wanted to find the error in approximating the sum with the first 4 terms, so my fourth partial sum, so when I plug in a 1, I get -1, and I get plus a 4th, minus a 9th, plus a 16th. Right? That's my fourth partial sum of the first 4 terms. This is that's approximately equal to the infinite sum. And how good of an approximation is it? Well, the error in that approximation will always be less than or equal to the next term in the sum, which is 1/25. All right, so a little more vocabulary for you. If you can say that the sum of the absolute value of every term, so you have no negatives, just anytime you have a negative, just make it positive. If that sum converges, we say that the sum is absolutely convergent. And if the absolute value diverges, but the sum itself without absolute value converges, we say that it's conditionally convergent. So let's use these new phrases to characterize these two sums. So this one, we'll call this one A. So sum A was -1 plus a half minus a third plus a fourth, etc. That sum we said converges because it's an alternating series and the terms are decreasing and going to 0. So this sum converges, but when you take the absolute value of every term, does that sum converge? No. 1 plus a half plus a third plus a fourth, that diverges. So this is a conditionally convergent sum. Okay. It does converge, but its absolute value does not. So this is called conditionally convergent. And then this other sum, call this B, was -1 plus a fourth minus a ninth plus a 16th minus a 25th. That sum converges. It's an alternating series. The terms are alternating signs, and the terms are decreasing and going to 0. So we know it converges. If I take the absolute value and I have +1 plus a fourth plus a ninth plus a 16th plus a 25th, does that converge? Yeah, that also converges. So this is called absolutely convergent because the sum itself converges and so does its absolute value. All right, here's some weirdness. If you regroup the terms in a finite series, adding up a finite number of numbers, the sum is the same, right? 1 minus 2 plus 3 minus 4 plus 5. I can add these in any order I want. I can put the 1 and the 3 together, and the +5 and the -2, and then the -4. And so I can do this sum in any order I want. So let's see, if I just do it left to right, I get 1 minus 2 is -1, plus 3 is 2, minus 4 is -2, plus 5 is 3. If I do it this way, 1 plus 3 is 4, plus 3 is 7, minus 4 is 3. Answer's the same, right? So this is just the associative property of addition. We can also regroup the terms in any absolutely convergent series, and the sum will remain unchanged. But mysteriously, this is not true for conditionally convergent series. So here's the alternating harmonic series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, alternating harmonic series. We know that this is convergent. But if we try to regroup the terms, right, so I take my first two terms and they go here. And then I took my fourth and put it here. And then I have my third and my sixth and they came here. And then I brought my eighth down and then I did a fifth and a 10th. So I'm just rearranging the order here. So just rearrange the order. And then if you do the stuff in parentheses, 1 minus a half is a half. A third minus a sixth is a sixth. Then I still have an eighth. So this becomes this. Becomes this. A fifth minus a 10th is a 10th. Right? So then I have a half minus a fourth plus a sixth minus an eighth plus a 10th minus a 12th. I mean, I can factor 1/2 out of every term there. When I factor a half out, this half becomes a 1, that becomes a half, that becomes a third. And I have 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. I have another alternating harmonic series. This is the series I started with. Is that kind of mysterious? Trying to figure out what this sum is, this infinite alternating harmonic series. I just did some, what I think is allowed math. When you do addition, you can change the order. You can add it up in any order you want. And I end up with half of what I started with. So the sum is equal to half of itself. And it turns out that by suitably rearranging the terms, you can make any conditionally convergent series sum to any real number. This bothers me. So you can't rearrange the terms, right? You can make it add up to any real number you want. All right, so I want you to try doing some work on these. Determine whether each series converges absolutely, converges conditionally, or diverges.